The Magellanic Clouds are the two largest satellite galaxies of the Milky Way, the Large Magellanic Cloud and the Small Magellanic Cloud. These two galaxies are gravitationally bound together and share a common envelope of neutral hydrogen, as well as several other common structures. Together, they form the Magellanic System. The large cloud is located 50 kiloparsecs from the center of the Milky Way, while the small cloud is 56 kiloparsecs away. Both galaxies are often classified as irregular, though the structure of the Large Magellanic Cloud shows some order, which makes it more accurately classified as a Magellanic spiral galaxy. Compared to the Milky Way, the Magellanic Clouds, especially the small cloud, have a higher mass fraction of interstellar gas and lower levels of heavy elements. These differences suggest the absence of an initial star formation burst, as in our galaxy, which could have led to the formation of a large number of stars. Recent studies using the Hubble telescope have allowed astronomers to determine the size of the halo of the Large Magellanic Cloud, which is about 50,000 light-years in diameter. This is 10 times smaller than the halos of galaxies with similar masses, which may indicate the influence of a collision with the Milky Way. According to lead researcher Andrew Fox, despite the loss of some gas, the galaxy is still capable of forming new stars, aided by its mass, which is 10% of the Milky Way's mass, allowing it to gravitationally retain the remaining portion of its halo. The dense halo of the Milky Way has significantly enhanced the blowing of gas from the Large Magellanic Cloud, leading to the formation of a gas trail resembling a comet's tail, stretching behind the galaxy. Researcher Sapna Mishra explains that the interaction between the galaxies allowed part of the cloud's halo to be preserved due to the significant mass of its central object. The pressure from the Milky Way will eventually cause the gas from the Magellanic Cloud to spill into our galaxy. However, scientists believe that not all of the gas will be lost, as the dwarf galaxy is gradually moving into open space. The unique position of the Large Magellanic Cloud makes it an important object for studying galactic interactions. Observing the impact of the Milky Way on the passing dwarf galaxy helps scientists investigate processes that occurred in the early universe, when galaxies were much closer together. The next step in the research will be to study the front part of the Large Magellanic Cloud's halo, where it is colliding with the halo of the Milky Way, providing an opportunity to more deeply explore the processes occurring during galactic collisions. How can radio telescopes reveal the secrets hidden in the most distant corners of the Milky Way? What unexpected discoveries might await us in regions that remain inaccessible to ordinary observation? Radio telescopes play a crucial role in studying the structure of the Milky Way, especially in regions where traditional optical instruments cannot penetrate. One of the most powerful and modern tools for observation is ALMA, Atacama Large Millimeter Array, a complex of radio telescopes located in the Chilean Atacama Desert, observing electromagnetic radiation with millimeter and submillimeter wavelengths. The telescope is designed to study processes that occurred during the first few 100 million years after the Big Bang, when the first generation of stars was forming. ALMA began its scientific observations in the second half of 2011, with the first images obtained from it being published in the press on October 3, 2011. Full operational readiness was achieved in March 2013. Although ALMA only started its operations recently, it has already contributed to many exciting discoveries and images. Thanks to it, the Sun has been photographed, an animation of planet movement around the parent star has been made, and the process of triple star formation has been captured. ALMA was also connected to observations around the black hole at the center of the Milky Way. The Event Horizon Telescope project obtained its first images in April 2017. In addition to ALMA, there are other radio telescopes that make significant contributions to the study of the Milky Way and the universe in general. One such example is the Arecibo Observatory in Puerto Rico, which was inaugurated on November 1, 1963, and operated until its catastrophic collapse in 2020. This telescope was one of the largest in the world, and was used for detailed analysis of exoplanets, as well as for observing phenomena at the Galactic Center and studying cosmic radio waves. It left an indelible mark in the history of science thanks to its outstanding discoveries. Arecibo helped establish the nature of pulsars by observing the Crab Nebula pulsar, which confirmed the hypothesis that these objects are rapidly rotating neutron stars. It later discovered the ultra-fast pulsar PSR 1937 plus 21, which blinked every 1.6 milliseconds. This led to an understanding of the mechanism of spinning up old pulsars through interaction with companion stars. Through radar observations, ice on Mercury was detected, hidden in the planet's polar craters. This was later confirmed by the Messenger spacecraft and raised questions about the possible presence of ice in the Moon's permanently shadowed craters. Arecibo also played a key role in studying Venus, penetrating its dense clouds with radar to map the planet's surface. In the 1970s, the first images showing volcanic and tectonic activity on Venus were obtained, and clearer pictures were made in 2015. Arecibo's measurements helped resolve the mystery of Mercury's rotation. It was previously thought to rotate synchronously with the Sun, but observation showed it completes a rotation every 59 days, explaining the even distribution of temperature on the planet's surface. The telescope's technologies allowed the mapping of asteroids approaching Earth. In 1989, Arecibo made a radar image of asteroid 4769 Castalia, revealing an unusually shaped object resembling a bone. These data help identify potentially hazardous asteroids to Earth and develop methods for deflecting them. In 1974, the observatory sent a powerful radio message aimed at a star cluster 25,000 light-years away. The message contained binary code depicting a human, a diagram of the solar system, and the basics of DNA, symbolizing a potential step towards contact with extraterrestrial civilizations. In 2012 and 2015, Arecibo recorded mysterious fast radio bursts, FRBs, which ruled out the hypothesis of their single-event origin, such as from star collisions. Their repeating nature suggested the existence of unknown cosmic processes. Another significant achievement was the discovery of the first pulsar in orbit around another star, PSR 1913 plus 16, in 1974. The fluctuations in the motion of this object became the first indirect evidence of gravitational waves, a phenomenon later confirmed and awarded the Nobel Prize in 1993. But what discovery at Arecibo caused a true sensation in the world of science? What if a random observation changed our understanding of the universe forever? The most significant discovery made by Arecibo was the detection of the first exoplanets. In 1990, it accidentally recorded the oscillations of the pulsar PSRB 1257 plus 12 caused by the gravitational influence of 3 planets. This breakthrough in the search for worlds beyond the solar system marked the beginning of the exoplanet research era. What new perspectives will open up with the development of next-generation radio telescopes, and will they unveil even deeper secrets of the universe? The use of radio telescopes has allowed astronomers to observe and study regions where stars and planets are just beginning to form, as well as areas hidden by dust clouds that optical light cannot penetrate. Thanks to these technologies, we can more accurately determine the composition of interstellar gas, study magnetic fields, and monitor the dynamics of star populations. However, radio telescopes not only help study the structure of our galaxy, they also open new horizons in the study of dark matter and its impact on galaxy dynamics. They continue to unveil new, previously inaccessible areas of space, and each launch brings new knowledge about how galaxies, stars, and planets are structured. What hidden secrets of the Milky Way could be revealed by future radio telescopes? What mysteries lie within the gas and dust clouds where new stars and planets are born?